We're going to continue with differentiation of logarithms. We're going to apply it to curve sketching. Before we do so, we'll just do a quick review what we did last time. Last time we learned this formula about log, that if you differentiate log x, ln x, you get 1 over x. If you differentiate log of fx, you write the derivative on top over fx. Okay, that's the rule. You may use the product rule sometimes, or quotient rule. Sometimes you may have to use the log law to simplify the expression before you differentiate. That will make your differentiation easier. So today what we do is we're going to apply it to curve sketching. So I'm going to sketch this graph, 3x times ln x. So to do that, we have to find the stationary point. To find the stationary point, we're going to using product rule. So write y equal to 3x ln x. On page 14, we're going to let u equal to 3x, let v equal to ln x, and use the product rule. Okay, so we'll do u dash equal to 3. V dash is what's derivative ln x? 1 on x, very good. So now we use the product rule. So write y dash is u dash v plus uv dash. U dash is 3 ln x plus u is 3x times 1 on x. Like that. And then the x and 1 on x gets cancelled, so we end up getting this. So we get 3 ln x plus 3. And then we have to find the stationary point. How do we find the stationary point? That's when y dash is 0. Point y dash equal to 0. And solve for x. So we have to solve a logarithmic equation. So write 3 ln x plus 3 equal to 0. And then you move the 3 to the other side. So ln x equal to minus 3. Ln x equal to minus 3 over 3. So ln x equal to negative 1. And now going back to the definition of ln x is log base ex. So when you solve a log equation, turn it into an index form. How do you write an index form? The index is negative 1, so you write e to the power of negative 1 equals to x. So that's the x value of the stationary point. Okay, after we do this, we're going to find the y value. Okay, let's find the y value. To find the y value, we'll sub it back into the original formula. Y equals to 3x ln x. And then substitute the x value in, which is this thing, e to the power negative 1. So replace x by e to the power of negative 1. And then you get 3 ln e to the power negative 1. Now, what's ln e to the power negative 1? It can be simplified using log law. So you get the negative 1 gets placed in the front. And what's ln e equal to? Ln e equal to 1, just 1, okay? If you forgot, you can always check with your calculator. So you can try that. So if you just press ln alpha e like this, you get 1. Okay. All right. So you get equal to negative 1, 3 e to the power negative 1. So you just get negative 3 e to the power negative 1. Okay. Or you can write that as negative 3 over e. So your stationary point is 1 over e, comma, negative 3 over e. That's your stationary point. Stationary point. Like that. Okay. Now we have to determine the nature. To do that, maybe we'll find the second derivative, because we have to find the inflection point anyway. So we'll continue. How much space do I have? There's this. Yep. No, that's all I have. Okay, so I use the upper part of the notes to do the second derivative. Okay, let's find the second derivative. So this is your... Oh, okay. Okay, so we're going to... Hopefully I didn't make a mistake. U dash B, U dash. Okay, that's fine. Okay, good. All right, so we're going to find the second derivative. So your y dash is 3 ln x plus 3. So your second derivative, ignore the 3. Differentiate ln x is 1 on x. Differentiate 3 is 0. So 3 over x. Okay. Okay. So, and then what we do next is we're going to substitute the x value of the stationary point. So when x equal to 1 over e, you get y double dash equal to 3 over 1 over e, which is 3e. That's which is positive. That. Now it's positive, so therefore we say it is a minimum. Okay, so this is a minimum stationary point. Okay. Minimum stationary point. So after we get the minimum stationary point, we'll now have to find the inflection point. How do we find the inflection point? We'll make the second derivative equal to 0. But if you write 3 over x equal to 0, you multiply both sides by the denominator, and you get 3 equal to 0, which is no solution. So it has got no inflection point. Okay, no inflection point. And then we'll try to sketch. Okay, let's try to sketch it. So draw the x and y axis. Okay, now before we do so, let's find out the actual coordinate of the stationary point. What would that be in decimal? Because it's hard to see how big it is without calculating it. So let's calculate what that is. So you can press Shift, this button, -1. You get 0.36 or 0.3 or about 0.4. Let's round it to 1 decimal place. And the other one, -3, -3 over alpha this, -1.1. Okay, that's where that point is. Okay. All right, so we're going to plot that point. That's a minimum stationary point. We should also find the x and y intercept and the domain of the function. So this is your y. So we should write down what the domain is. Now, what's the domain? What's the restriction on ln x? Well, it has to be greater than 0. Good, very good. So that means we only have a graph on the positive part of this. There's nothing in here. Okay. All right, good. What else are there? X has to be positive. We'll have to find x-intercept. X-intercept. Now, how do you find x-intercept? We make y 0. You write 0 equal to 3x ln x. That means 3x is 0 or ln x is 0. Now 3x is 0 means x is 0. How about ln x equal to 0? Write it in index form. So you write e to the power 0 equal to x. X is equal to 1. Okay. Now can x be equal to 0? No, because x has to be positive. So you cannot accept this solution. So it's only one x-intercept, which is 1. Okay. Now that means I don't need this part of the graph, so I could just draw it so that I just include the positive part. Okay, so let me draw this again. So you don't need the negative part of the x-axis because the domain is all positive value of x, y, like this. All right, so you got 1, 2, so I'm going to make 1 a bit bigger so that we can see. So I'm going to put 1 here, 2 here, like this, 3. And the same scale, 1, -1, like that. All right, let's plot the stationary point. Remember, your stationary point is this. That's a minimum, 0.4, -1.1. So it's around here. But when you write it, please write the exact one. So write the exact value of the stationary point, but use a decimal value to locate the location of that stationary point. Remember, it is a minimum. Now, what's the x-intercept? 1. So x-intercept, and there's no y-intercept because x has to be positive, so there's no y-intercept. Okay, so what you do is, all right, now it's not defined as 0. Maybe we should look at the behavior of the graph near 0. So let's make x approaches 0 on this graph, 3x ln x. So what you do is just use your calculator to do that. So make x equal to 0.1. So you do 3 times 0.1 ln 0.1. What do you get? -0.69. How about you make it even smaller? -0.13. So as x approaches 0, it's approaching, what's the function approach? No, it's not infinity, it's getting smaller. It's not getting bigger. It's -0.00. Yeah, it's approaching 0, isn't it? Normally, ln is approaching -infinity, but in this case, it's actually approaching 0. So you always have to test this. So it's approaching 0. So there's a point here. It's approaching this point, 0. And you also look at the behavior when x goes to infinity. See if there's any horizontal asymptote. So we can check this by substituting a very large value. So you do 3 times 10 ln times ln 10. Right, gets bigger. And if I put more, yeah, it gets bigger, right? So there's no horizontal asymptote, so it just goes to infinity. Okay, now we're ready to sketch, so it must look like this. Yeah. Right? And we can see from the second derivative, it's always positive, right? The second derivative is that it's always positive for a positive value of x, so it's always concave up, minimum. Okay? So that's your graph. All right, any question? You should be able to attempt the question from the textbook on curve sketching. And today what we're going to do, we're going to differentiate bases other than e. Okay, so we're going to differentiate 2 to the power x. We'll try to find a formula. Yeah. It's not exponential, it's like log, ln x. It's ln x, 3x. From 0 onward, you just, I don't know. Actually, I've got a way to find out. Let me go to Explorer. There's a way to find out. Okay, let me show you something. Let's pause this for new recording. Okay, next page, you ready? Next page. All right. Okay, now, so what we do is we're going to differentiate 2 to the power x. Now, we did that last time with differentiation by first principle. Do you still remember what that equal to? When we differentiate 2 to the power x. I think it's about 0.69 times 2 to the power x, isn't it? We'll try to find a formula for that because it's very hard to remember. So in general, when we differentiate a base other than e, you'll get a constant times a to the power x, isn't it? where k is a constant. And the reason why we use e, because that constant is 1. So when we differentiate e to the power x, it's just 1 times e to the power x, isn't it? So today we want to find a formula for k. There's actually a formula for k. Okay? We'll now try to find a formula for k. Okay, so before we do that, we need to do some investigation. Use your calculator to evaluate the following. Can you do this on a calculator, see what you get? If you need to borrow one, I've got some here. Okay, all right, good. Now use your calculator, calculate what that is. So you're going to do E, no, it's pause. Okay, now have a try. So press e to the power of ln 3. What does it give you? I have to close the bracket. Give you 3. All right. Now predict what will happen for the next one. All right, let's see if it works. So we'll change it to 5. Oh, it does. Okay, looks like there's a formula. Looks like that if I apply exponential and log, they cancel each other out. So whatever that is, if we apply exponential log, just become f of x. Or in other words, I could express any function in terms of exponential. Just write e to the power of ln fx. We're going to use this formula to help us to differentiate. Does it have to involve e? Yes, it doesn't have to. So if your base is a, then your log has to be base a. So you get that. So for example, if I do 10 to the power of log, say 5, it will give you that, right? But however, if you use ln with 10, it doesn't work. So if I go power, if I do ln 5, it doesn't work. It has to match. So the base there has to match with this base for it to work. Okay? So basically, example, I could do 10 to the power of log base 10. Both have to be 10. You will get 5. Right? Okay. So now we have this important formula. But this is more important. We're going to use this to help us to differentiate because we know how to differentiate e rather than differentiating 10. Okay, so we're going to do that. But before we do that, there's another thing I want to talk about. Okay, how do I remember all this? It's actually quite easy because you apply log to a function and then you exponentiate the result. You're going to get back to fx. So they cancel each other out. So you apply log first and then exponential, or if you apply exponential first, then log, you still get fx. Now you can see how this one works because if I do it over here, e to the power fx, the fx by the log goes down, isn't it? And what's log base e? 1. Like that. So you can see why. So both. So you can think of log base e and exponentiate by e. They are inverse of each other. They cancel each other out. So in both cases, regardless whether you apply log first and exponential or exponential first then log, you get the same answer. So we can try that. So if I do ln, shift that to the power of 5, it gives you 5. Okay, it gives you 5. All right. After we do this, then we're going to do some examples to practice. Okay. All right, so simplify this. So log base e to the power x, you can bring the x down. You can bring the x down. Yeah, log base e2. Okay. So for the next one, using the rule, actually, I still wanted to do the same thing. Okay, e, that x there goes down. X log base e2. Right, just applying the log law, bringing the power down. Bring the power down, bring the power down. Okay. All right, okay. Now, we can actually prove it. And the proof is not examinable. Let's try to do a proof why this works. So proof of y log e to the power of log base e fx. Why does it become fx? There's a proof. Okay, so to prove that, what you do is try to think how it works. I forgot. Okay, but have a try. Let me see. Y equal to fx. Yeah. Okay, we'll start with y equal to fx, and then we're going to write down log base e. Let's log both sides. We're allowed to do that. Log base e, log both sides. Like that. And then what do we do? Now, let's recap this rule. If I write log base e, a equal to b, right? I could write it in index form, e to the power of b, e to the power of b equal to a, right? This one's well known to you. So we're going to do the same thing. We're going to write this in index form. So we can write this e here, to the power of this equals to y. Get the idea? I'm just applying this rule now. But remember what y is. Y is exactly this. This is y. So I proved this is fx. So I proved it. Okay, all right. Proof is not important. You just need to remember this important formula. Okay, we're going to use this formula to help us to differentiate 2 to the power x. So we're going to do that on the next page. And then we'll do a summary of that. Then you do some worksheets and the textbook questions. Okay. Okay, next page. Already change the color of the pen. Okay, next page. Okay, now we're going to differentiate. To help us to do that, let's review how to differentiate the first one. Actually, don't make it too big. Okay, how to differentiate e to the power 2x. What's the rule? You differentiate 2x, you choose 2, right? Agree? Do you remember? You differentiate the power times by itself. Yes? Good. What if I want to differentiate ln this thing? What's ln2? It's a number, right? So if it's a number, you do the same thing. So if I differentiate this, what do I get? ln2. Agree? Times by that. Does that make sense? Because it's just a number, ln2. So it's the same rule. Regardless I differentiate e to the power 2x or e to the power ln2x. They're both numbers. So when you differentiate it, you just get the constant in front. Okay, how about differentiate e to the power x? You just get e to the power x, right? Good. Okay, now how does that relate to this function? Well, it relates a lot. Let's see how that works. So now remember this rule. Let me write it again. Hopefully it's still recording. I hope. Okay, good. All right, so remember this rule. F of x, let me write it again. You should write it, is e to the power of ln fx. Agree? That's the rule we just discovered. We can express any function in this way. So therefore, I could express 2 to the power x as e to the power of ln 2 to the power of x. Agree? I could express this thing and just put it in the new position. Okay, all right. Now, what do we do with the log law? We can bring that x down. Yes? Log law. Good. Now remember, we haven't differentiated yet. We just move the x down, right? So let's write e ln 2. Write that as a coefficient of x. This is still y. Now how do I differentiate that? Did we just do that question before? Have we differentiated already? It's over there, right? We can just use that. This is just that thing. We just differentiated it. ln 2 e to the power of ln 2x. Now, what is this thing? This is y, isn't it? And what's y? 2 to the power x. So now it's become 2 to the power x with the ln2 in front. Now, if you try to do ln2 on a calculator, let's see if it gives you 0.69. So if you press ln2, it does give you that number we've seen before. So that constant is actually related to the log of the base. So comparing your answers, so if I differentiate e to the power x, I get this. But if I differentiate 2 to the power x, I get that extra number in front. And that's the formula for that number. Okay, any question? Hopefully it's good. So now we can differentiate, we can also integrate as well. So we'll do the same thing with integration. Okay, so I'll give you a minute to write it down. Okay, good. All finished. Okay, good. Let's move on to integration. So exactly the same thing. How do I integrate e to the power 2x? What do I do? What's the formula? 1 over 2. Yes? Still, is that known to you? That's known. Good. It's on the formula sheet. So if there's a number here, you just divide by that number in front of x. And what if you integrate that? You do 1 over ln2, right? E to the power of ln2 x. And by integrate e to the power x, you just get e to the power x plus c. And all of these are related to the integral of 2 to the power x. So like before, we're going to write 2 to the power x as e to the power of ln 2 to the power x dx. And what do we do with the x? We bring the x down, right? So we're going to write integral e to the power of x ln 2 dx. And this is just doing this question, isn't it? It's the same question as that. So when we integrate that, you do 1 over ln2 e to the power of x ln 2 plus c. Right? This is just this question. But what's e to the power of x ln 2? This is just 2 to the power x. So you can write that as 1 over ln 2 times by 2 to the power x plus c. So when we integrate 2 to the power x, we have that extra constant there. Okay? All right, let me put it on the bigger screen. Okay, good. All right, let me just draw a line there so you can see. Okay, good. Right, so compare and contrast. So when you have 2 to the power x, you have that extra ln2 there. Okay. All right. We've got one more thing. How about differentiating log with a base other than e? We're going to do that as well. Differentiating log other than base e. Okay, let's go back here. Okay, now revise change of base law. What's change of base law? Log base AB is equal to log base CAB over log base CA. That. Okay. So we're going to use the change of base law to help us to differentiate log base 2x. So we're going to write log base 2x. Let's write it in terms of log base e. So it becomes log base ex over log base e2. The reason why we do this so that we can differentiate log base ex, right? So let's write it in terms of ln x over ln2, which is same as writing 1 over ln2 multiplied by ln x. Now we can differentiate log base 2 because I could just differentiate ln x, isn't it? With an extra constant in front. So when we differentiate, so if I write d over dx, log base 2x is same as differentiating 1 over ln to ln x. And what's the derivative of ln x? 1 on x with that extra constant. And then to make it look nicer, you put the x in front of ln. Alright, that's how you differentiate log base 2. And same for any other power. Now we have a complete list of differentiation, which I'm going to summarize on the next page. And then we'll do some examples, then you do some practice question after this. Okay, already? Alright, we're going to summarize, and then we'll do some examples, and it's going to be very... Right. Okay, good. So, we're going to summarize this. Okay, on your book. Okay. Alright, next bit. Differentiate e to the power x. What's derivative of e to the power x? Is just e to the power x. But when you differentiate base other than e, you get ln a times a to the power x. See the difference between them? You get that extra ln a in front. And when you differentiate e to the power fx, it's f dash x e to the power fx. And when you differentiate a to the power fx, it's just the same thing. You do f dash of fx, a to the power fx, but you only have to add ln a in front, like we did here, right? So it's very simple. Now, unfortunately, these two are not on the formula sheet, so you need to memorize. Only this is on the formula sheet. That's on reference. Okay? But it's very easy to remember. You just have to add an extra this. So if I look at this formula, I could adapt it to this. Just put an extra ln a. Okay? All right. How about integration? Same thing. Integral of e to the power x is e to the power x plus c. Now, if you do a to the power x, you still get a to the power x, but you divide by ln a plus c. Right? You got that extra. And integrate that, you get 1 over a e to the power ax plus b x plus b. And if I integrate that, you still get 1 over c a to the power cx plus d. But because it's a, you have to add an extra ln a at the bottom, just like we did here. Okay? Same rule, except we have an extra ln a. So when you differentiate, you times. When you integrate, you divide. Okay? Okay, good. All right, one more, which is the integration of differentiation of logarithms. So ln x is 1 on x. Derivative of that is f dash of x over fx. Like that. Now, if the base is a, you can use the change of base law, or if you just remember from before, you can memorize the formula f dash of x over fx. But because it's ln log base a, you have an extra ln a at the bottom. Okay? Or you can choose the change of base law to do that. Okay, we'll do some questions. Okay, let's do the first one. You can either use the method we showed before, I just use the formula. So maybe easier if you use the formula, just go y dash, 5 to the power x is 5 to the power x again, but you just times by ln 5 plus c, like that. Oh, oops. Thank you. All right. All right, next one, differentiate the next one. Same thing, you just differentiate it as if it's exponential. So you differentiate this, which is 2x times 7x squared plus 1. But because it's 7, you have to times by ln 7. That's the only extra thing you have to add. And the last one, you can just use the change of base law. I think it's preferred you just write it like this. Log base ln x over ln 5. ln 5, like that, and then differentiate. Okay, differentiate, get 1 over ln 5 at the bottom, times by the derivative of that, which is 1 on x. Okay, and make sure you put the x in front of ln 5, so it reads better. Or you can write that as 1 over ln 5, but put a bracket around it so it doesn't get interfere with the x. Okay, and if you write it like this, that will be wrong, because that could be written as 5x, which is not ln 5x, it's ln 5 times by x. That will be wrong. Okay, good. Alright, we've got some integration. Have a try using the formula we just learned. Alright, try the integration. Alright, integration. Same thing, you just divide by, to get 6 to the power x, so you just divide by ln 6 plus c. Very easy. And this one, same thing, you do 6 to the power of 3x minus 4, but you times by 1 over 3, using the rule that we learned before, like that. But because it's base 6, it times by also 1 of ln 6 as well, like we did here. Right? So you can clean that up to write that as 6 to the power 3x minus 4 over 3 ln 6 plus c. Okay? Alright, good. So we did that. So today you do the exercise from the textbook, finish the remainder of exercise 4.7, as well as a worksheet that I will give you in a minute. Okay.